Okay, so let's shift to the next talk by Sunita Chandrasekaran, and her title is the best practice for the productive yet performance software development. Sunita, are you ready? Hi, Sunita.
Yes,
Good to
thank
see
you,
you
Dr.
again.
Sun.
Okay,
Good to see you too.
so please, yeah, okay, so please go ahead.
Okay, thank you. Oops, me go one slide behind. All right, greetings everybody, and thank you very much for joining. And thanks to the conference organizers for making this happen. No matter where we are sitting, and we're able to do this virtually, so that's a big deal. So thank you very much. Right, so this talk is going to be about the best practices for the productive yet performant software development, and it's going to focus on experiences gained via many projects that has been going on in my group, and the different mistakes we have made. And what I'm trying to do here is please don't repeat what we did, right? So we can do this better. I also wanted to give a shout out to all our funding organizations for making several of these projects happen, and to my group, the wonderful set of students that I've been working with. That is my CRPL group back in here in University of Delaware. Okay, so here are some best practices. Obviously, you would think there is many more, but I think I have a little story per best practice based on what we had observed while trying to get real world big code applications running on large scale systems. So to kick off, the very first application of interest is a biophysics problem. This is work in collaboration with chemistry, biochemistry department at the University of Delaware. And as you can see here, the problem is about a nuclear magnetic resonance, a vital tool in structural biology and biochemistry. And it measures chemical shifts, and we could predict the chemical shift, and the prediction of the chemical shift of protein structures are important for drug discovery purposes, but the prediction was happening for many hours, and by that I mean over 10 hours or more than 10 hours. So our goal was to find a way to accelerate the prediction of chemical shift of protein structures, and to that end we started off with a code from Ohio State University, a C code written for the algorithm for the biophysics, and it has never been parallelized before, never been accelerated before. So it's basically written for that particular algorithm. And also this prediction of chemical shift is something that is quite important in many big molecular dynamics code. So one of our motivation was, what if we were able to accelerate this code and bring it to a amount of time taken, and then other big molecular dynamics code could call this function and be able to perform operations way faster. So that was our motivation. And I want to mention that this was work done by two undergraduate students with no parallel computing experience before. So we started off with 6 months of training, little benchmark codes. When you work with students, I tend to set expectations which are probably more than what could be really handled. But then you tone it down, you adjust to the circumstances, you figure out how far you can go, because high performance computing incurs a lot of training curve, right? So there is quite a bit to learn before you can really use programming models, just like Honor Mutlu was talking about in the previous presentation. There is a ton of things to be aware of before you can really move code to big platform. So the very first thing we did was profiling, and that is one of the best practices we're talking about right now. So you could use gprof, you could use perf, you could use nvprof, and now Nsight Compute, Nsight Systems. You could use Tau, Scorpy, Vampire. There are a dozen tools there that will first let you probe into your code to see where is the most compute intensive hotspot in your code that you want to focus on, and that should be parallelized, accelerated on multi-core GPUs. Without profiling, you simply cannot dive into hundreds to thousands of lines of code and nail down the function that is of importance, right? So here we first did serial profiling, and what you can see is different pies, which are different functions in the code. And the most interesting part we deciphered was the little pie that you see, which took 23%, was just a serial code that could have been written better, right? And this I'm saying this with a lot of caution here, because the code is written for biophysics. The code was not written for multi-core or GPU platform. So there is a reason why it was written that way. And as a computer scientist, we jump in and we look at the serial portions of the code and we try to, for example, iterations called within a loop that didn't need to be inside the loop. So you hoist it out of the for loop, so you stop calling it 100,000 times, right? So this particular Pi, which took 23% of the compute time, was just a serial code that could have been written better. So by cleaning up the code, we got rid of the Pi. And then the different Pis in the previous slide that I readjusted, and now we have a newer problem to solve, right? So jumping directly into results here, so by cleaning up the code, by making it more easy for parallel multi-core and accelerators, we were able to use OpenACC, which is a directive-based programming model. Plug in the different pragmas, different directives in the various functions as and when needed. And the crux of it is we were able to bring down 14 hours of time taken in the serial unoptimized code. If you look at the last row, we're looking at about 47 seconds. So that was a huge speed up, and we couldn't have done it without profiling. And the undergraduate students graduated, they became my PhD students, and we also published this in PLOS Computational Biology, a nice interdisciplinary science story to communicate to the biophysics community that we can go faster than a code that is running for 14 hours. So profiling, that's one of the best practices that we learned, and the students loved to see the aha moments of, oh, now my code is running so much faster. How did I do it? Profiling. So that was one story. The other story is best practice with what we learned for systematic testing. This is an interdisciplinary project with NCAR, which is National Center for Atmospheric Research in Colorado here in the US, and Max Planck Solar Society in Germany, and University of Delaware. So the three-way collaborative problem. And here, the little box, I should have thought about this. It's basically an animation of solar flare. It's not going to run now, but the bottom line is it's basically accelerating the solar flares in a way that we are able to perform computations close to real time, depending on how fast the scope that is receiving data is able to store these data and is able to send these data to the computations. So there is this multi-million-dollar NSF installed telescope, and there are going to be images from the telescope that we're going to receive. So can the software really process such abundance of data in real time? So that was a challenge. And for this too, we have used the open directive-based model. This is work with 4 computer scientists, 2 physicists, another challenge in interdisciplinary science because we speak 2 different languages. So many phone calls, many interactions to understand where the problem is. But the fun part is, when you figure out the science of it and we figure out where exactly we could help, improve the code, the real fun begins, right? So here, this was a code which, the work which is over 3 years now. And the issues we had were, as and when we were trying to parallelize the code, we figured out that there were issues in the compiler. So we logged bugs with the software team, PGI, NVIDIA, OpenACC compiler development team. And there was another important lesson learned here was we used diverse hardware. We used something in UD, we used hardware in NCAR, we used another hardware in Max Planck, because you want to move on beyond one platform if that platform is giving you issues, because then you want to test if there's an issue with the platform, is there an issue with the compiler, is there an issue with the library, are there issues with different software versions of the compiler? So there could be many things. So having a diverse software hardware platform definitely helps figure out where the problem is. And we reported compiler runtime bugs to OpenACC compiler development team. And in the process of the past 3 years, we have used incrementally improved versions of the compiler, evidently performing better than the versions we were using in the year 1 of this project. Then we also were reporting ambiguities in OpenACC specification because as a user, we interpret the definition of the programming model features differently than what was indeed in the specification. So a lot of clarities happened in the process. Then the most important hurdle we had was verification issues. And this MURAM code had about 7 parameters where the values of these, or the accuracy of these 7 parameters, had to fall within a threshold, else we are affecting the science. So what we had initially done is, try to maintain a threshold, and we had tried to figure out, where the accuracy problems were. But imagine 4 computer scientists, right? And imagine each of them are tackling different pieces of the code, and there's a version control maintained, but somebody is committing into the version, person is committing into a version control. There are different commits. We need to make sure what commit everybody is working on. There is time difference. We are in East Coast. NCAR is in Mountain Zone. Max Planck is in Germany time zone. So there were a ton of logistic issues, and at the same time there was a bug which took us forever to nail down, because we had not maintained a good verification protocol, if you like. And not just compilers and software, there were also domain decompositions as part of the code. You can, you can create different decompositions, domain decompositions, depending on how many processes you want, depending on how many nodes you have, depending on how many GPUs you have per node. And every time you come up with a different optimization in the code, you need to verify if the optimized code is correct, right? Before you can scale it up to multiple platforms. So these were the logistic issues. And of course, when you're dealing with acceleration and parallelization, you're going to have issues like register occupancy. Are you really using up to the theoretical performance that the GPUs can offer? Then there are many kernel launch overheads, which means you don't want to launch many kernels because there's going to be overhead. So can you cluster some of these kernels, right? And then there were noticeable MPI communication. So these are the optimization issues to tackle. There were verification issues to tackle. There were software and hardware issues to tackle. So lots of reporting, bugs, and issues throughout over the past 3 years. And then the lessons we learned was, why don't we build a Jupyter notebook, to capture and record the divergence of results between a serial core, between a multi-core code, between GPU code, right? We're dealing with 3 different versions. So when an optimization is pushed into a commit, there is OpenACC on multi-core, there is OpenACC on GPU. So there are 2 different versions. So we need to check against the Jupyter notebooks if the verification is meeting the threshold. And initially we got excited because it's a wonderful code to work in, and we started to commit bigger changes, optimizations to the code. And then we realized that this is becoming hard to debug, right? Because when you optimize your code, you're applying many different optimizations, and then when there is an error in the verification, you don't know how to track it. So then we retraced our steps, and we went to many commits behind. And this is the thing I would like to call could have been done better. And then we went back and we added optimizations one at a time. Transpose was one optimization. Ray merge was another optimization. Loop integration was a third optimization. So instead of clustering everything together, we unwrapped it and we folded it one by one by one. That became easy for testing, right? And documentation. Oh goodness, people, please, let's document things properly. Because you want to look back at your code 3 years later and figure out, what did you do 3 years before? And if you don't document, you're going to spend cycles after cycles after cycles deciphering what you did. So we did a mistake, and then we went back, and then we retraced our steps. We started making the documentation crazy. Then the experimental setup, going back to the diverse software, hardware requirements and platforms, because every time we changed a platform, we found a newer bug, a newer issue. So when we put the code out, an open source code, many solar physicists are going to use the code for their own development or whatever. So we need to make sure that it is running on multiple platforms correctly, right? So we can't be confined to the platforms that we have access to. So we set up several other platforms, including one from Jules from Ulish. So we had about 4 to 5 different platforms to make sure that the code was working correctly, and that really helped narrow down the bug. Optimizations, yes, only after a thorough verification of the serial or the base version do you start to optimize, right? If you have issues from the get-go, you don't add optimizations to the code. You want to make sure you have a stable code. Then at the end, we did see decent results with respect to 1.73x speed up on a single NVIDIA Volta 100 versus a 40-core Skylake CPU node, and this is work in progress. This is an overall new RAM code, but there are important pieces like radiation transfer function, magnetohydrodynamics function. So now we are going individual function by function and trying to see how we can individually increase the speed up to overall, up the speed up. So there were a lot of lessons learned, and this was one of my PhD students on the project who I think learned a great deal of how do you do, a good software engineering project. Voila! So we did get to publish, and this was a wonderful moment for us because, as you can see, the tweet that I put out when we submitted, we were really happy because this was work done after 3 years, lots of phone calls, lots of bugs, lots of issues, but we managed to, figure out the right steps, right protocols, and this is published and presented just last month at the ACM PASC conference. Moving forward, report bugs. Now, I cannot insist how important it is to report bugs and not always come up with workarounds. Bugs need to be reported for the compiler or the software to make it a better place for the next person using the software. So a story there is, this is an ongoing project to prepare a plasma physics code. Pecan GPU stands for Plasma in Cell. Code, which is in collaboration with Kasus in Germany, which I see is one of the sponsors of this conference, HCDR, Georgia Tech, University of Delaware, Oak Ridge, and so all of us are together working on preparing this Pecan GPU for Frontier, which is being built at the Oak Ridge National Lab, the first exascale system. And the goal here is whatever code, Plasma Pecan GPU that ran on Summit is running on Summit, which is the current system at the Oak Ridge National Lab. And in the top 500, this is ranked second. The idea is to come up with 4x times whatever we're running on Summit to Frontier. Frontier is being built. So we are using baby Frontier systems to figure out, how do we get to Frontier when it is really in place, which is very likely to happen the end of this year. And this is of a massive interest to Oak Ridge National Lab. It's part of a project called CAR, Center for Acceleration Application Readiness, where we are one of the 8 teams in the United States chosen to help port and figure out what are the nitty-gritties, what are the issues, moving such a massive piece of real-world application from Summit to the upcoming system Frontier. So you can imagine the amount of issues and challenges we could run into. I also want to take a moment to give a shout out to our collaborators as well as AMD, HPE, and Cray, whom we have been bombarding with a ton of emails and bugs to work together to get the application ready. So here, I think a major lesson learned was report bugs, right? Because we are trying to prepare OpenMP offloading code. We are trying to prepare OpenACC code. We are trying to prepare Alpaca, which is a C++ abstraction created by HCDR Germany. And it has subthings including CUDA, HIP, SYCL, etc. So we are trying to improve Alpaca to target HIP backend, which is AMD software, and Frontier is going to be AMD CPU, GPU system. And we are working with AMD vendors, we are working with HPE Cray vendors, bugs reported on OpenMP offloading with AMD Cray HPE compilers, and as well as HIP, software stack. So we come up with workarounds because that is an easy solution, right? But we don't want to, always come up with workarounds because, that's not going to be helpful for somebody else jumping into the software. So we want to make sure the software is stable. And we also want to make sure that there is compatibility. There are dependency issues between different packages we've been using on the baby Frontier systems. So report, and the entire team has been extremely helpful to make sure that the bugs are sorted out. And we create a ticket in ticket systems. Obviously, the best practice is not to email runtime and compiler errors. You want to put them in a proper system so there are people looking at it, the vendors are looking at it, and at the same time the team commits a lot of code. Any code committed by one person obviously should not be reviewed by the same person. It's a common sense, right? So we want to make sure that there are PR requests and there are others incrementally reviewing code changes. And there are time critical bugs sometimes because we are on a clock. When Frontier is delivered, we have to make sure Pecan GPU runs. So we directly interact with the vendors, bypassing the track system only when there are time-critical bugs we need it sorted out. And at the same time, this is also a good application where we are trying to create little benchmark codes, because Pickle GPU is massive, right? And if you want to figure out if a particular optimization is working, you don't want to run 50,000 lines of code. You want to probably write a test code to check if that particular optimization is really doing its job. So we're also creating little benchmark codes and things, and that becomes an easy problem to tackle by the compiler vendors, because we're giving them a sample problem. We are giving them a reproducible, which vendors love, because they want to be able to look at an example code where the compiler really fails. So giving them sample problems is excellent, and it's very time effective. Okay, so then I have 3 to 4 more, which are kind of stories based off many other projects we have done, and I'm trying to condense some lessons learned. I think all of us know about containerization and Dockerization. What you see is training materials that my student and I with NVIDIA had put together on OpenACC. And we have GitHubs, we have slides for teachers to use so we can save some time. But what NVIDIA did was they Dockerized the entire teaching module. And now that helps, because if you're teaching and if you have homework assignments to give your students, then you can totally get the entire bundle, use Dockerization, and not worry with the different dependency packages, issues, and things. So Dockerization has also helped, especially when you have applications that are needing different software packages, one working on one system, another working on another system, so on and so forth. So the next best practice is, and this is again another big project, which is exascale computing project Solve. So my group is in charge of the OpenMP validation, verification, test suite, where we build test codes to validate and verify OpenMP offloading compilers. So this is part of the bigger ECP Solve project. So as you can see, OpenMP specification is over 500 pages, right? So there are many definitions, and the features are getting updated into the specification as we speak. We started off with 4.0, now we are in 4.5, 5.0, 5.1. There's also going to be a 6.0 if you like. So features are being added as we speak, compilers are being developed as we speak. So how do we really test that the compilers can really compile a particular code? And what are the compiler errors? What are the runtime errors? So that's what this project is about. And as you can see that little circle, somebody reads the specification, somebody writes the code, somebody commits the code, somebody reviews the code, and then we put it out. There's a GitHub, and it's open source. The entire project is open source. Then we get PRs from other developers as well as other users, which really helps, because in a way we are getting feedback. But you can see there is a process, right? There is a ton of things going on. There are 2 people in my team, but there is 2 people from Oak Ridge team, and there are other folks that would, do PRs to the software. And this is also work in collaboration with a number of people. So more the hands-on in a project, the project is prone to errors, prone to more bugs. So it's important that everything is coherently maintained, especially when you have more than one person working on the code. And I'm just looking at my notes here as we speak that I wrote, to communicate for this particular project. Pre-commit, continuous integrations and tests, and writing little tests. And this is all code that are either validating, verifying an individual feature of OpenMP, or a combination of features in OpenMP, or we orphan a particular feature and test only that pragma. So there are many varieties of code happening. There are many compilers involved. There are more hands-on, and there are many platforms. Right now, this is running on Summit. It's running on those baby Frontier system. It's running on NERSC Cori systems, some of our internal UD systems. And so there are 4 to 5, and there is a web page. If you look up ECP Solve, anybody interested in OpenMP validation suite, you will look at the table that we create, which has a list of what failed and or what passed. Now, the best practice here, as I said, there's a lot of automation in a way going on with respect to infrastructure. And there is some maintenance also going on. We use GitHub for collaborative environment, and then there is issue tracker. Like I said earlier, you want to record issues in an issue tracker system, which keeps tracks of bugs and fixes, because this particular project requires that we consistently test upcoming compiler versions, right? Sometimes we get beta compiler versions to test, not really open to public, but just for us to test them out. So we want to see what was a bug 2 months ago, or say 6 months ago, and what is a new compiler version, and did this bug really get fixed, or is it leading to something new at this point? So the issue tracking really helps. And then pull requests. So my student commits, a code, another student checks the code, another user does a pull request. So there is a GitHub repository definitely maintained, as well as history. We are maintaining a website to list all these efforts. So there's a one-stop shop to go check info on this ECP Solve VNB project. And that website also has publication, presentations, and everything. And most importantly, we also developed a coding standard, because it's an open source project, it's an exascale project, it's time critical, so we need help. At the same time, we don't want somebody committing a code that is completely out of sync with the rest of the codes that we have created. So that we have developed a coding standard, a template that people can use when they add code to the repository. So automation really helped with that project. And the next one is documentation. I think it's it's only obvious that we need to document every step of the way what we create, because in a student developed project, students graduate, right? Good for them, they should graduate. So now the project is developer less, and another student jumps in and wants to pick up from where we left, because maybe a 6-year project, or it's a master's student graduating in 2-3 years. And if the project is well documented, it's easy for somebody to pick up from where it was left. If the project is well documented, it is easy for you, for us, to go back and check, what did we do 2 years ago, right? So highly important. And there are many ways you could document. Something my students really like is Jupyter Python notebooks, and I also find it interactive. You have these different cells. You could even use Google Colab to create these Google Jupyter notebooks. And we share it among the group and outside the group as well. And by hitting run in those little cells you have in the Jupyter notebooks, you can interactively communicate to the user what you're doing in every step. So if a mundane hashtag comment is boring in a C code, find a different way. But we need documentation, and we have suffered a lot for not doing due diligence in documentation in all the projects that I just mentioned to you. And I think last but not the least is pair programming. And many things come to mind here, but what I want to actually tell you guys is about, you might have heard of gpuhackathons.org. If you haven't, it's a good time to go check out the page. Basically, there are many hackathons happening across the world, and some of my students have participated as mentors and participants. And what I've really observed is when he or she is sitting with another person together, they seem to be making a ton of progress, which is typically not the case when you're confined by yourself, because you are playing all the different permutation combinations of the code by yourself. So pair programming has helped in a way that the first project I told you about, the biophysics, the students were working with, undergraduate students were working with 2 PhD students, with myself and the PI from chemistry. So there was lots of hands-on, a round table, many people sit together. You can see in the image, there are 2 people, sitting together, and there's more on the table, and it's usually a team. And you ping pong and you divide and conquer the problem. And it doesn't really need to be a hackathon, right? We could do this as part of a flipped classroom, for example. Projects, if there are 2 people in a team, 3 people in a team, they tend to, and if it is the right kind of team, they really tend to make fast progress and learn a lot. So hackathons have been very helpful to go check out, how do you really get a real world application running on a large scale system as a team. So definitely check out this site as well. So that's pretty much a summary. That's my group in action, although this was when the world was normal and we were in person in our labs. And so that's a summary you see. But beyond that, I also want to mention agile development, right? Setting realistic contribution, then having diverse hardware software requirements, writing small tests to make sure that your optimization, your compilers are really doing the job, continuous integration, code review, incrementally reviewing the work, not just looking at 20 commits together because you might miss something. And when it comes to education and training, I think flipped classroom can be a really nice adoption when we are trying to do lots of hands-on. So thank you.
Thank you very much, Sunita, for the great talks. So we have one question. Maybe my voice is echoing. Please. Okay. Anyway, so there are one question from Clement Lau that how can the HPC community help in education of code developers to learn basic issues that would help them with the first steps of the execution efficiency?
Can you repeat the first half? I didn't quite get it. Apologies.
Okay, so there that maybe that I mean I think that he means that so there your analysis and the stepping is very good, but of course not many people can ask you for your direct help. So how the HPC community help in the education of these code developers? Is there any
Right,
good
right.
systems or community?
Right, right. That's an excellent question. Thanks, Clement. I think it has to be only done incrementally. Again, like I said, HP is field, right? And there are so many things that needs to be learned before we can really do high performance computing. So I think the education and training also starts in classroom. So today's next generation, the today's students would be the next generation workforce. If we all teachers do do the job of communicating these best practices in software engineering and software development as dedicated or dedicated capstone projects or things, I think that's a stepping stone. And participating in hackathons, like I mentioned, it does help to bring a sort of a principle oriented, coding, because you're working with five other people, right? You're there for 5 days and you have two mentors. So my students always come out of these 5-day hackathon with a ton of better ways to do software engineering. So I would recommend to participate in these community driven events because that helps to make you accountable for doing things correctly, because somebody else is going to be affected if we drop a best practice.
Okay, so here's one more question from Marek. That do you think that it's possible to it is some interesting question. So do you think it is possible to build code from start as a parallel construct bypassing any sequential stage? So
That's a
writing
very
the
good
parallel
question.
code
Thank you for
directly.
asking. Yeah, yeah. So we are currently dealing with a code like that, which doesn't necessarily have a sequential code. It somehow landed up that we only have the parallel version, right? And oftentimes we have wondered that, oh, if we had the serial code, could we have started off in a different place? Could we have had a better parallelized code? We don't know. But at the same time, the biophysics code that I mentioned was a serial code. And I think at that time it was completely under our purview of how do we take the serial code, how do we clean it up, how do we add parallelization to it, and we could go from the start, right? And we didn't have to rely on an already parallelized code. So I would much rather prefer a sequential code, but it's not always possible. So I think we have to deal with whatever we got the best. But we also have to make sure that the parallelized code could be written for a platform that was 10 years before, right? So there is room for improvement, there is room for profiling and performance analysis for how it could be modified for today's platform. And it's hard, it's definitely hard.
Okay, so the last question from me. I'm sorry. I'm very curious that how the Oak Ridge and Summit users port from the CUDA and the OpenACC to OpenMP for AMD GPU. Is there any strategic scheme or something, Mana?
Yeah, thanks for asking. That's another challenging time we are in, right? So yeah, Summit has been using OpenMP, OpenACC, CUDA, and other pieces, but it's NVIDIA driven, and Frontier is all going to be AMD. But I believe and I can see that there is a lot of effort going on amidst the AMD HPE vendors to help prep the code. It is not easy, as we can already see our pick on GPU is definitely a challenge, but we have been trying to work on this project since September 2019. So we have come a long way, I would say. We are far ahead of where we were when we started, because back Alpaca, which the Pecan GPU core uses, could run on the then AMD cards, but the current AMD cards have fantastically improved, which means Alpaca and the HIP backend also has to improve. So I believe there's a lot of back and forth going on between ECP applications and car codes, a lot of back and forth conversations with vendors. There are hackathons happening to help the application developers do that transition, because it's many things are new, right? Even the interconnections are new. Input output a deal. How do you deal with that? That's new. So yeah, there is multiple challenges, and I think as a community we have to come together to make this happen.
Okay. So thank you very much. So our time is run up. So thank you again to Sunita.